with a current of 80 milliamperes. So now we're talking about electric current and resistance. So if a current of 80 milliamperes exists in a metal wire, how many electrons flow as a given cross section of the wire in 10 minutes? How many electron flows as a given cross section of the wire in 10 minutes? And in what direction do the electrons travel with respect to the current? In what direction do the electrons travel with respect to the current? So let's take first here, let's make a diagram. So here I have my wire. Piece of wire. And then I have an electric current. Let's say that it's going in this direction. And that electric current is just 80 milliamperes. Remember that I mentioned in classes that the electric current, the direction of the electric current is taken from the positive terminal of the battery to the negative terminal of the battery, but the electrons that are the free charges that are moving to the conductor, they move from the negative terminal to the positive terminal. So really, the electrons here are going to be moving in this other direction. So let's say what direction the electron travel with respect to the current in the opposite direction. Now, they want to know how many electrons just pass through this area in 10 minutes. So what we know about current, we know that the current is the variation of charge that passes through a given area in a given interval of time. This is the most basic definition of electric current. Remember that the units of electric current are the amperes, and the ampere is just coulomb per second. So if I know the electric current and I know the time, what I need to do is to find the amount of charge that this 10 milliampere current, sorry, this 80 milliamperes current representing that amount of time of 10 minutes. So we say that I times delta T is equals to delta Q. So milliamperes, 80 milliamperes is 80 times 10 to the negative 3 amperes. So we say that this is 80, no, 80.0. 80.0, so times it again. 80.0 milliamperes. So it's 80.0 times 10 to the negative 3 amperes times delta T is given in minutes, but the current in amperes is in coulombs per seconds. So if I want to get coulombs, I have to spread this 10 minutes in seconds. So I would say 10 minutes times, to make the conversion from minutes to seconds, now 60.0 seconds that I have in 1.0 seconds. So that is going to be equal to delta Q. So now, I'm calculating delta Q easily. We get that delta Q would be basically 48.0 coulombs. 48.0 coulombs. Now, I don't want to find the magnitude of the total charge that passed through the area in these 10 minutes. I'm going to find how many electrons rose to that area. So I have to find the number of electrons. So if you have the total charge that passed through the area, and of course you also know what is the charge of one electron, if you want to calculate the number of electrons, the only thing you have to do is to divide that total area delta Q over the charge of the electron. So you divide the total, the total charge delta Q is total charge delta Q. You divide the total charge delta Q over the charge of Q. So you get this is 48.0 coulombs divided by then the charge of one electron is 1.602 times 10 to the power of negative 19 coulomb per electron. The coulombs are going to cancel out, of course. We're going to get that the number of electrons when you divide this, it will give you 29.96 times 10 to the 19 electrons that you can round to 3.00 times 10 to the 20 electrons. I got it using three figures exactly as this number and this number is supposed to be coherent with the number of figures. So this is 3 times 10 to the 20 electrons. We found the total number of electrons that are passing through that area. I would like to explain one more exercise now. There is an exercise about the current and the resistance and the resistivity. So let's see the next exercise here. So they say a ball mirror connected across the terminals of a tungsten filament light bulb measures 150 volts when an ammeter in line with bulb registers a current of 0.522 amperes. So we must find the resistance of the light bulb, and we must find the resistivity of tungsten and the bulb operating temperature. If the filament has a coil length of 0.600 meters and the radius is 2.30 times 10 to the negative 5 meters. So basically, what we have is a circuit where this here an ammeter connected in series with a light bulb. It's going to be basically like a resistor. Okay, so this is going to be my light bulb, a tungsten filament. Now, I will just connect a voltmeter here in parallel to measure the voltage, the total voltage across the light bulb. And of course, if there is a current flowing here, there should be a battery. Let's change, let's show the plates. So there should be here a battery but they don't mention uh, basically anything about the battery, but which uh, basically anything about the battery, but which suppose we know that there should be a battery there. So in a way that we can have. Now, what this voltmeter measure? A voltmeter measure the drop of voltage across this light bulb. And that should be indicate that there is only one resistor, the same drop of voltage across the battery, right? So we have the drop of voltage here in the battery. Well, this voltmeter is measuring, a drop of voltage of 150 volts. At the same time, a ammeter is measuring a current of 0.5 to 12 amperes. So we have a resistance over here, that is the resistance of the light bulb, and this is what we want to find, the resistance of this light bulb. So we're going to use the Ohm's law. And I will say that the current that flows the circuit is equal to the voltage divided by the resistance. So I can calculate the resistance if I say resistance is voltage divided by current. So if I divide the voltage by the current, I have 150 volts divided by a current of 0.5 to 2 amperes. And that will be 220.3 ohms. So the resistance of the light bulb, the tungsten filament of the light bulb is 220.3 ohms. Now, what they say after that, they say find the resistivity of tungsten under both operating temperature if the filament has an uncoiled length of 0.6 millimeters and the radius of 2.30 times 10 to the negative 5. So that means if I extend now the filament, the tungsten filament, right? And we have basically like a kind of wire when I extend it. If we have a length of 0.600 meters, and it has an area, cross-sectional area. If it's a radius, then it's circular. We have a radius equals to 2.30 times 10 to the negative 5 meters. So we have to calculate the area, this cross-sectional area, and we know that it's pi times the square of the radius. Why? Because in my equation to calculate the resistivity, that this is what they want to calculate, resistivity, is a property of the material of the filament. I know that the resistance is equal to the resistivity times the length divided by the area. So if I want to calculate the resistivity, we say that the resistivity is resistance of the area, divided resistivity times length. So we have that the resistivity will be resistance times area over the length of the wire or filament in this case. I know the resistance because I found over here. I know the length because it's given over here. I don't know the area, so we calculate the area. We know the area is pi r squared, so it's pi times 2.30 times 10 to the negative 5 meters. Squared. So the area will be approximately 16.61 times 10 to the negative 10 meters squared. I will just work with a value like that. And I don't have to write that in scientific notation because it's an intermediate calculation. So now we just substitute that area to calculate the resistivity. So I say resistivity, the resistance of 220.3 ohms times the area that is 16.61 times 10 to the negative 10 meters squared over the length, which is 0.600 meters. So if you calculate now the value of the resistivity would be approximately 6.1 times 10 to the negative 7 ohms. So this is the value of resistivity that I have for this uh, tungsten filament on the light. So this is a problem that combines the Ohm's law and also combines, what is resistance, what is resistivity. Remember that the resistance depends on the geometry of the conductors, and the resistance is a measure of the position in the flow of current, that the conductor will make. Why the resistivity is a property of the material, so the change from material to material is, let's say, the opposite to conductivity. So materials with high resistivity have low conductivity and vice versa. The conductors are supposed to have good conductivity or high conductivity and low resistivity. So the wires that I use, to conduct electricity that are made of copper usually. But in the case of the light bulb, the idea is to have that tungsten filament a high resistivity instead of a high conductivity, because the high resistivity is what is gonna make really the filament to glow. So I need a high uh, resistivity in this case, and a high resistance to make the filament really to glow, or to be brilliant, right?